Hello class. If you got a hoodie, you notice 4 equations on the front of it. Newton's third law, Newton's second law. You may have not noticed that that's orbital velocity, and that super long equation. Well, that super long equation is it's Russian, so Siklovsky's rocket equation. I'll just call it the rocket equation. But basically, what it tells you is how much you can change your velocity wherever you are in space, whether on the ground or in orbit. As you can see here, I've tried to replicate the plane in a game called Kerbal Space Program. Now, Kerbal Space Program is a physics simulator of rocket science, and a pretty good one. However, it is not a realistic one-to-one scale to real life, but Kerbal Space Program is actually 1/10 of the scale of real life. Also worth noting on Kerbal Space Program is that everything is ideal. What I mean by that is the engines always burn at 100% capacity, propellants are always burned 100% all the way, and so on and so on. As in real life, there are problems such as fuel slosh, the engines actually exploding. There are a million things that can go wrong in real life, but in Kerbal Space Program, everything is perfect. Now on that note, let's see me fly this into space. Now that we're in orbit, we can calculate how far this spacecraft can go by finding the ISP of the engine, gravity of Earth, or in this case Kerbin, the natural logarithm of the initial mass and the final mass. Now the ISP of the engine, for what it says in the game, is 345, and the gravity on Kerbin is 9.81 meters per second squared. Multiply that by the natural logarithm of the initial mass, which is 20.17 tons, that's metric tons, and divided that by 15.925 metric tons. Now, the wet mass is the current wet mass, and the dry mass is what happens when all the propellant is used up. Now, by plugging in all the numbers, we find that the change of velocity is 799.76 meters per second. Now let's test that calculation. Right now, I'm setting a maneuver node that'll equal to 799.76 meters per second. Now what I'll do is I'll try to burn at the maneuver, and the engine will run out close or almost to 799 meters per second. As you can see from the orbit, I was 1.1 meters per second off. That tells us that our calculation was near nominal. But after that burn, our Kerbinauts are now stranded in orbit around Kerbin. Through the power of quick save, I now put my Kerbinauts in a suborbital trajectory to land at the Kerbal Space Center. It is worth noting that in the rocket equation, g is the gravity of where you're at. Since we're in orbit, gravity is less due to it being further away from the planet.
How you brought this girl into our bed. In clearing your name, you have ruined our lives. Do you know what Angelica said when she read what you'd done? She said, you've married an Icarus. He has flown too close to the sun.
As a great pilot once said, a landing you walk away from is a landing indeed. I hope you can take away from this video and that you learned something about that hoodie. Thanks for watching.